concurrent lines, a circumscribed or an inscribed figure, and then that whole circumcenter business from yesterday. What's up, John?
Is the circumcenter just for the three angle bisectors?
Watch your mouth.
The three perpendicular bisectors?
Correct. And not only that's half of it, knowing that it's where the three perpendicular bisectors meet. The other half is, well, why don't we just talk about it right now, because that was my next topic. So we learned yesterday, and Gianna just went over this with you, that the perpendicular bisectors of a triangle are all concurrent, which means they all meet at a point called the circumcenter. And I said that's half the battle that you won. The other half of the battle is what's so special about it? Okay, I get it. It's formed by the perpendicular bisectors. That's half of it. The other half is what's so special about it? It is equidistant from the vertices. Thank you. It is equidistant from all three vertices. All right, so that's both parts of the circumcenter I need you to know. Formed by the perpendicular bisectors, equidistant from all three vertices. And maybe it's manageable right now, but today I'm going to throw 2 more points of concurrency at you. There's more than the circumcenter that lives in a triangle. I'm going to throw 2 more at you today, 1 more at you tomorrow. All right, so let's go to the assignment. Anything you want to ask? Anything we want to look at? I know I put my answer key up. Anything with the circumcenter or perpendicular bisectors? Or just vocab in general? All right, I'm going to take your word for it that we're okay. Please, every day I'm just going to beg you, literally beg, don't let it snowball out of control. Okay, all this vocabulary that we're throwing at you. Even the best students have trouble here because they don't keep up with the vocab. All right, let me see your work real quick. And you didn't have any problems on it last night, but make sure you can construct the circumcenter. So I throw a piece of paper in front of you that's just got a triangle on it. Find the circumcenter using constructions. You're able to do that. Okay? You should be able to do that. Thanks, everybody. All right, so right off the bat, yesterday we learned the perpendicular bisectors were concurrent. Let's find out a new set of lines that are also concurrent other than the perpendicular bisectors. Grab your compass for me. We are going to review how to do an angle bisector because that's got some special meaning in these triangles. So what we're going to do on triangle ABC, we're going to do all 3, not 2, all 3 perpendicular bisectors, all 3 angle bisectors coming from A, B, and C. So I'll do one with you coming from B, and then you do A and C on your own, and then you tell me what you notice. So review on how to do an angle bisector. I'm going to bisect angle B right now. A reminder, when you're doing the constructions, try not to have these huge arc marks because then you guys get nuts. You're like, where do they intersect? Where do I put my straight edge? Have them nice and small as you possibly can handle. All right, so I put my compass point on vertex B. I make an arc that intersects angle B in 2 spots. As you guys remember, the first arc is always usually for intersection points, which gives me 2. Now I take my compass, I go to each point of intersection, and I make 2 more arcs that I need to intersect each other. Don't care if they intersect the first. The first one's just there for points of intersection. So I put my compass point on both points of intersection, make 2 arcs that intersect. Look how nice and tiny that is. And then grab a colored pencil for me, please. Grab a colored pencil. I want all 3 angle bisectors to be in different colors so you can see them. Grab a colored pencil, highlighter, line it up with vertex B, and draw in your first angle bisector. And then I'd like you to do them from angle C and angle A now, and see if we notice anything. about the angle bisectors in a triangle? You don't need anything huge. Nice work, guys, making those arcs smaller. Nice work. Looks a little cleaner, doesn't it? Again, make them as small as you can. Right? All right, what are we noticing here, guys? All three angle bisectors are what? What do we notice on your diagram and mine as well? When I drew in all three angle bisectors, they are? Can we use a nice vocabulary term? They are all concurrent. There you go. Here's our conclusion. Ready? So conclusion, all three angle bisectors in a triangle are concurrent. So wow, now we just added angle bisectors to perpendicular bisectors. So now there's two sets of lines, right? Two types of lines that are concurrent. Perpendicular bisectors and now angle bisectors. Yesterday, what did we call that point of concurrency with the perpendicular bisectors? That was called the circumcenter. Now, with the angle bisectors, we have a new name for the point of concurrency. That point right there, many of you saw that intersected as. Yesterday was the circumcenter. Today, we call that point of concurrency the incenter. That's called the incenter. All right, the incenter. Yesterday, circumcenter, what did we know about it? I know it was formed by the perpendicular bisectors, but it was also equidistant from the vertices. Incenter's got a special fact as well. The incenter is equidistant from the sides of the triangle. Okay? It's equidistant from the sides of the triangle. All right? So for our diagram down here, do me a favor. Here's what I'm going to give you. Given. It's not a proof, don't worry. Point D is the incenter of triangle ABC. Okay? Point D. Point D is the incenter. So now let's see how much power that gives us. Watch what we can label on the diagram right now. Well, first of all, if it's the incenter, that means what's CD, AD, and BD? Those are all what? Good. Gabby, say it again. Great. They're all angle bisectors. So that I'm not going to do it at all the angles, but because point D is the incenter, that allows me to say those two are equal, right? And I'll only do it one more time. Those two are equal because I know incenters formed by angle bisectors. What else does it tell me? Well, I know the incenter is equidistant from the sides of the triangle. Somebody give me 3 segments in that diagram that are now congruent. 3 segments. Go ahead, Doyle. What's good? Awesome. There you go. DE is congruent to DF, is congruent to DG. Perfect. Just by knowing that's an incenter, look at how much we just marked on the diagram. Just like yesterday when we did perpendicular bisector in the circumcenter. We know a lot of information. We just got to keep it organized and straight in our mind. Any questions on the incenter and what's so great about it? Because I have to move on to new vocabulary now. We're all good? Going? All right, next up. Let me introduce you. That's the same slide. An altitude. Okay, an altitude. New vocabulary term in a triangle. An altitude. I think in the middle school, I don't think you used the term altitude, did you? I think you used the term height of a triangle. Height is the altitude, all right? In the high school version, it's called the altitude. And here's what it is. An altitude is a segment in a triangle that must start at one of the 3 vertices. It can't start on one of the sides. It has to start on one of the 3 vertices and must be drawn, where's my word? Perpendicular to the opposite side. So if it's got to be drawn perpendicular, what am I going to form here at ADB and ADC? Right angles, correct. Altitudes form right angles. But the biggest thing is it has to start from a vertice. It's not an altitude if it starts from a side. So, a little bonus question here, honors kids. How many altitudes exist in every triangle? Not infinite. What does every altitude have to start from? A vertice. So how many altitudes exist in every triangle? 3, because there's 3 vertices, correct. All right, let me show you a special type of altitude. Because everyone thinks, they're always inside a triangle, inside a triangle. Let me show you a unique one, and then I'll go back up to the conclusion here in a second. Anybody know? I'll give you a little hint. This angle is slightly bigger than 90. What type of triangle do I have on your paper? Obtuse, thank you. This is an obtuse triangle. Be careful when you're dealing with an obtuse triangle and altitudes, and you'll see why. So here's what I'm asking your help with. Construct an altitude from point A. All right, so vertice A, construct an altitude. So before I grab my compass with you guys, I know altitude, it's going to start at A, and it's got to be what to the opposite side? It's got to form a right angle, right? Does that look like it's going to form a right angle? No, I don't think so. How about that? Does that look like it's going to form one? Where the heck is this bad boy going to be? That doesn't look like it's going to form one. So how in the world am I going to do this? You ready? Let's find out. Grab your compass. Let's figure out how to construct an altitude. And the hint I'm going to tell you, you already know how to do it. Altitudes have to be what to the opposite side? Perpendicular, right? So, and you don't have to draw this. I don't know if you remember a line and a point off the line and doing a perpendicular line through it. That's exactly what we're going to do now. First step, compass has to go on point A. So put your compass point on A. And you guys need to somehow open up your compass so that intersects BC in how many spots? Anybody? 2. Let me know if anybody can do that. Because if you can do that, you would be a math magician. You should be up here with the pen. Anybody? Not going to happen, right? Not going to happen. I did make a suggestion if that ever occurred, if I can only get it to intersect at once, but I need twice. Anybody remember my suggestion, Matt? Extend the line we're trying to draw it through. So everyone grab your straight edge. Let's make BC a little longer so I can do this. Yes, let's make BC a little longer. Anybody starting to see where this altitude's going to be? Won't be anywhere inside the triangle. It's going to be outside. All right, so now that you've extended BC, go ahead and make your arc. Intersect BC in 2 spots. Let's see, can I? 1, 2, looks good. Again, that arc is just so you can establish 2 points of intersection. And then, yes, from both points of intersection, draw 2 more arcs that should intersect each other. Line up your straight edge with vertex A, and you'll notice when I'm dealing with an obtuse triangle, at least one of the altitudes will be outside your triangle. Outside your triangle. All right, so just a heads up there. All right, why don't you try it now from vertex B to AC. Draw your altitude from vertex B to AC now. Because there's a reason I'm introducing altitudes here. There's got to be a reason. So from B to AC, everybody. I think we can get this. We don't need to extend it. Nope, we can get it to intersect AC in 2 spots. And your opening of your compass does not need to be the same for the last 2 as it was for the first. If you want to make it smaller for the last 2, that's fine. Got a little problem though. I'm trying to show you guys that these are concurrent, that the altitudes all intersect at the same spot, but doesn't look like it on my diagram. Any suggestions here? Yeah, see if, yeah, just make them a little longer, right? I want you guys to see that they will. And I don't want to make our diagrams a mess here, all right, but they will be concurrent, okay? So we know that they'll intersect right down here. So again, if we did draw, and I'm not going to do that, I'm going to save you time because I want to get to the assignment. But if we drew it from C to BA, I'd probably need to extend BA and do C also outside it, right? And they would all be concurrent. So it needs a name, right? Because I got circumcenter, I got in-center. This one needs a name too. And I don't have a blank spot. So point of concurrency. Is it EY? I don't know. I don't care. Point of concurrency for the altitudes. Ready for this one? Circumcenter, in-center, altitudes, orthocenter. Oh, it sounds like orthodontist. Yep, great. Good job. Yep. Orthocenter. I do have some good news. Perpendicular bisector, equidistant from vertices. In-center, we just learned today, equidistant from orthocenter. No fancy fact. No fancy fact about the orthocenter. But you are responsible for something with the orthocenter. And that's our last topic here. I need you to know where it's located based on the type of triangle. Okay, based on the type of triangle, the orthocenter is going to be here, here, here. So there's 3 types of triangles I need you to be aware of. First one, acute triangle. Second one, obtuse. And anybody know the third one based on its angles I'm going to have you do? Right triangle, yes. Okay, well, can we fill out obtuse? Because we just did that one. If a triangle's obtuse, where would the orthocenter always be located? Somewhere on the outside of the triangle, correct. So if it's obtuse, your orthocenter will be somewhere on the outside. What about acute now? Acute. Think about it. Here's an acute triangle up here. Can I draw, let's see, I can draw that inside. Well, any of the altitudes have to be outside for an acute. Nope. So where's the orthocenter going to be located? Inside. And here comes the controversial one, the right triangle. Buckle up, honors kids. Right triangle. First thing, quick review. Orthocenters where all 3 what intersect? Oh. What did we just go? All 3 what? Altitudes, right? Somebody describe to me what an altitude is in your best vocabulary. What is an altitude? Starts where? It has to start at a vertex, a vertice, and be drawn perpendicular to the opposite side. Everyone take a look at this right triangle I have up here. So you just told me an altitude's got to start at a vertice, right? And be perpendicular to the opposite side. Isn't it already drawn? Isn't this one of the altitudes right here? Perpendicular to the opposite side? Yeah. Hey, that's an altitude right here. One of the sides of a right triangle is an altitude. Hey, do you see another one up there that I don't have to draw? That starts at a vertice perpendicular to the opposite side? You see another altitude? Starts at a vertice perpendicular to the opposite side. There's the second one. Do we know where the orthocenter is going to be now? I don't need to do the third one for the hypotenuse. Where's it going to be? Where's that orthocenter going to be? Where do these 2 intersect? Right here, right where they meet at the right angle. So I can't say it's going to be outside. I can't say it's inside. How do I describe this one? It's actually on the triangle. All right, and make sure you know what we're talking about with on. Right there. Okay, it's gonna be right there. We good? So there's no special fact about an ortho center, but I do need you to know where it's located based on the type of triangle. All right, I gave you a little hint for the first problem, number 27. Let's get out the textbook pages because I'm giving you guys plenty of time here. What's up, Ian? Sure. You guys got to 11:40. A little under 20 minutes. Let's get it going, please. Let's get it going. Have we covered it? Then it's fair game. Correct.